Welcome to The Explainer. Today, we're unpacking a really groundbreaking study, one that basically challenges everything we think we know about global green building standards. If you've ever walked past one of those shiny, modern, sustainable buildings and thought, wait, does this design actually make sense for the environment it's sitting in? Well, you're exactly in the right place. We're going to dive into some fascinating research recently published in The Property Economist that takes a hard, honest look at the reality behind these green certifications. So let's just jump right in. Think about two completely different ideas of what makes a building green. On the one hand, you've got that high-tech narrative. You know the exact one I'm talking about. It's all about slapping solar panels on the roof, putting in low-flow faucets, and using recycled cladding everywhere. Literally regardless of whether the building is sitting in the middle of the desert or deep in a rainforest. On the flip side, you have the ideal of bioclimatic design. This is the idea that a building should organically react to the sun, the wind, and the local weather. Our central mystery for today is this: which of these two approaches is actually driving the global green building industry? All right, here is our roadmap for the explainer. We'll start with the green building myth, then look at a massive test of 750 certified projects, dig into the energy-climate connection, explore the disconnect with water and materials, tackle the hot and humid problem, and finally, talk about fixing green certification rules. Let's get to it. Kicking things off with part one, the green building myth, or technology versus bioclimatics. We really have to ask ourselves, should a sustainable building just copy-paste generic tech everywhere, or should it adapt to its specific local environment to actually be efficient? That adaptability is the core of the bioclimatic ideal, and honestly, it's the very foundation that the EDGE certification system was built on. Now, EDGE, which stands for Excellence in Design for Greater Efficiencies, is this major green building certification created by the World Bank's International Finance Corporation. It's huge, deployed in over 140 emerging markets. To actually get this certification, a building has to prove a 20% reduction in energy, water, and embodied materials compared to a local baseline. The whole assumption here is that because the baseline is local, the certification inherently rewards climate-responsive design. But does it really? Moving to part two, testing 750 certified projects through the KNSD's global investigation. To find out if reality actually matches this wonderful bioclimatic ideal, we finally have something better than just architectural theory. We have a massive, and I mean massive, international data set. Researchers at the Kwame Nkrumah University of Science and Technology analyzed 750 EDGE-certified projects. And we're talking a global scale here, spanning all 14 ASHRAE standardized climate zones, from the incredibly sweaty, humid tropics of West Africa all the way to absolutely freezing, snow-covered environments. They tracked every major climatic variable, temperature, humidity, wind, and cross-referenced all of it against the actual reported savings of these buildings. Now, the researchers went into this with, strong theoretical reasons to expect climate to act as the steering wheel for all green building outcomes. It makes sense, right? And while the data did confirm their expectations, it did so with some massive, totally unexpected caveats that kind of fracture how we've been viewing resource efficiency up to this point. Which brings us to part three, the energy-climate connection and the big data reveal. Okay, so the researchers uncovered a literally massive disparity in the data. We're talking about R-squared values here, which is essentially just a fancy way of asking how much of the building's savings can be directly explained by the specific climate it sits in. Well, it turns out climate is a genuine, really robust driver for energy savings, explaining 20% of the variation. But for water and materials, the numbers just fall off a cliff. Climate explains a mere 5.6% of water savings and an absolutely abysmal 2.3% of material savings. The environment barely even registers for anything other than energy. So focusing just on energy for a second, this creates what researchers call a U-shape of savings depending on where you are on the map. It's super interesting. In the extremely hot and dry zones, think intensely arid, baking deserts, buildings hit massive mean energy savings of 57.5%. And in the freezing cold zones, they also perform incredibly well, hitting nearly 50%, mostly due to all the heavy insulation. But right in the middle, those hot and humid zones, the savings plummet to around 31.5%. You see, the architectural strategies being used in these places are entirely different depending on the environment. In hot, humid zones, architects use a ton of heavy in-situ concrete. They rely on thermal mass to soak up that persistent heat, and they pair it with ventilated roofs to let the heat eventually escape. But move over to a hot, dry desert, and the playbook completely flips. They use lightweight insulation and aerated blocks, because without all that moisture hanging in the air, the building can just cool off rapidly the second the sun goes down.
So for energy at least, architects are genuinely designing according to the climate they build in. The theory actually works. Whether it's shifting to air-rated blocks in the desert or packing in plasterboard and heavy insulation in the freezing cold, the building's thermal envelope really is responding to the sun, the wind, and the temperature.
But what about the rest? Let's get into part 4, the water and material disconnect, where we see a totally different logic entirely. Right, so for water and materials, we discover a completely different reality. The data shows that the climate you're in, the rainfall, the humidity, the heat, dictates almost nothing about how much water or material you save. Literally almost nothing. Instead, these choices are driven entirely by human governance. It's all about cost norms, what structural typologies local contractors are used to building, and just plain old specification habits. Basically, people build with what is cheap and familiar, regardless of what the sky above them is doing. Climate has totally negligible explanatory power here. In fact, sometimes it works backward. The study found that hotter average temperatures were paradoxically associated with lower water savings. Why? Well, probably because the sheer demand for outdoor water use just spikes when it's scorching hot, which completely wipes out any efficiency gains you get from those fancy indoor low-flow fixtures. And for the physical materials used to build the structure, the climate models explain essentially zero. This brings us to a major hurdle in Part 5, the hot and humid problem, also known as the tropics penalty. 35.1%. Guys, over a third of this entire global data set, hundreds of certified green buildings, are located in the very hot humid zone. This includes booming places like coastal Ghana, Accra, and Tema. So those difficulties we saw earlier with the U-shape of energy savings, they aren't just some weird statistical outlier. This specific problem affects a massive, massive portion of the world's emerging market construction. Think about the last time you were in a really muggy, humid city. You can basically think of humidity as this heavy, wet blanket. In a dry desert, you block the sun and boom, the building cools down. But in a place like coastal Ghana, the persistent moisture in the air traps latent heat. It literally structurally limits how much energy you can save just by designing a clever, passive building envelope. You could design the absolute best ventilated roof in the world, but that blanket of humidity means you are going to hit a hard ceiling on your energy savings way earlier than someone building in a dry desert. But, and this is a really vital but, it's important to note that this tropics penalty only applies to energy. Achieving 50% savings in water or materials in places like Ghana is absolutely possible. The climate isn't stopping them at all. The data actually shows that when these regions underperform in water and materials, it's purely due to local building habits. It's a lack of active cost optimization for structural materials and just a general unfamiliarity with low-flow plumbing technologies among the local contractors. So, how do we solve this? Let's jump into Part 6, fixing green certification rules and the policy implications. This study shines a huge spotlight on a structural flaw in how we measure sustainability right now. Systems like EDGE require a uniform 20% minimum savings across the board, literally everywhere in the world. But come on, asking for 20% energy savings in a dry desert is far too easy. Buildings there routinely hit 50% or more without breaking a sweat. Meanwhile, asking for that exact same 20% in a humid tropical climate, that is a serious, demanding stretch. And for water, having a blanket 20% rule completely ignores regions where water is severely scarce and demands much, much higher conservation. So the logical next step is for frameworks like EDGE to implement climate-differentiated thresholds. The system has to be fair, and it has to be truly effective. First off, policymakers must acknowledge that the climate structurally limits energy savings in the humid tropics. Second, they need to demand much higher water savings in arid climates where water is actually a precious, scarce resource. And finally, they should adjust material savings thresholds in cold zones, recognizing that those buildings genuinely just need to use more physical material to hold all that heavy winter insulation. We now have hard empirical proof that the environment fundamentally changes what a building can and cannot achieve. So I want to leave you with this. If climate truly dictates how buildings perform, why on earth do our global green standards still demand the exact same results everywhere? Thanks so much for joining me on this explainer, and definitely keep questioning the standards around you. Catch you next time.